Okay, we started recording. So what you should see on the screen is what we typically have when we start out, which is on your desktop, you have problem set 7, you have the name of the problem set, and you have the number of the problem set. I like to keep it standardized. It's just something called workflow. Another piece of jargon is modularity, which is just simply to say when you're ever doing anything, you want to make sure that you have some sort of repetitive process, because if you're anything like me, you'll forget a lot of things. And for me, it's a weakness. I always have to write things down. In this case, modularity refers to the fact that the format of our problem sets are sort of have a similar process as we go on. So I like to encourage you to use your desktop on your machine, simply because you'll see it. You won't forget about it. So just you right-click, you create your own folder like this, and then you just type problem set 7. Try not to put spaces here. I've looked at some students' homework on their desktops, and they put spaces in their file names. The reason you don't want to always do that is why it's a bad idea in my view, is that because it's hard to tell how many spaces there are. So you always want to tell your computer clearly where it wants to go, because it's a pretty persnickety thing, in the sense that if you want to tell your computer that your homework belongs on your desktop, you want to make sure it's here. I'm saying this because I have helped students with this issue before. And as you see here, you see I just dragged and dropped the data set. This is actually a .r data file. You won't see it, but you'll see the type here, R data, and then you'll see the script, the R file. And this is the code. This is the data set. So I'll walk you through this problem set and this time around. So let's just open up our RStudio. Actually, I probably already have it loaded because I've been debugging this before. So we'll take a look. Okay. Yeah, I have a bunch of stuff open, so I'm going to clear it, and I'll show you what it looks like when it's empty first. Yeah, we want to clear everything. Okay, my computer's complaining because I closed a bunch of files, and it asked me, "Are you sure you want to do this?" I said, "Of course, I do." So, this is what happens when you open R, of course, right? There is no project. I think it's always important to actually even read some of this stuff here. There's actually a newer version of R that I saw on the listserv, 3.3.2. So if you want to get the latest version, you can do that, but it's not important at all. Let's see if there's anything in our environment. We see that that's clear. You want to use that little broom just to make sure you clear everything there in your history. So let's get started. Okay, so what we're going to do is we're going to open a file. It'll ask me where to go, and I'm just going to go to the desktop, and we're going to go to, oh heck, we'll do this. I'm actually going to just close R right now, because if you set it up correctly, as we did in the first week, you should be able to open your script first, and it'll open up into a new version of RStudio. And in fact, if you see right here, you'll see that the path file is set right here too. You kind of see it in like a very clear kind of gray lettering, right? Users desktop problem set 7. That's actually the path file. And the reason it's clearer to read is because there are no spaces there. And if you look at this location, you'll see, oh look, we have the 2 files that we need. How do we know that? Because you can go to the Files tab. I often use the dir function. If you do get working directory, it'll print what you actually see just right above here, right there. See, that's the same thing right here. And if you want to do the dir function in the console, it's a directory function, it'll give you the names of those 2 files that you see right here. This is interesting because even though R is a programming language, we gave you sort of a wrapper. RStudio is a wrapper, so it doesn't even feel like a programming language. So I've spoken with some students who are adept programmers and will say, oh, R is not a programming language. Au contraire, it is a programming language. It developed out of Bell Labs. It started as came out of the S language, I believe. If I have a book on it, I would show it to you. But seriously, it's a serious programming language. Okay, let's get started with the problem set this week. As usual, you can just highlight and run the script. So let's just do that. And we're installing our package, the Mosaic package, in the Mosaic library. You'll see the red lettering. There's nothing to worry about. I'm going to show you. There's a window of it downloading. It's always good just to make sure that you install the package. And then we'll install what are called dependencies. Dependencies are simply other kinds of packages that are required as you install this. Oh, look, interesting. So it looks like we got a little bit of a warning message. I don't think this is a grave issue. But if you notice, when I talked about the newest R version, it looks like Mosaic actually adapted with the times, and it is actually for version 3.3.2. I think we're going to be fine. I don't think we're going to run into any problems. It's always good to keep sort of up to date with the versioning, but we're not going to run into any problems when we deal with that such a small update like that. That being said, it's pretty good to update. We can talk about that later. Yeah, what I'm going to do right now is we're going to actually do a little bit of the sampling distributions. This is a neat little function, plot dist. What does this show you exactly? Well, the first one is these are actually just sort of, in a sense, hypotheticals. What it does is it tells you to plot a type of a distribution. Statistics is all about distributions. What is a distribution? Well, it's a shape of the data, basically. A normal distribution is, it's kind of a misnomer. Why is it called normal? I don't know. It's not. There's nothing normative about it. You know, if we think about psychology, I remember taking a class when I was an undergraduate. We took abnormal psychology. So I don't even know if that's even a PC term anymore, and because it assumes that, you know, other forms of psychological behavior are normal. Well, banish that thought, and this is a tricky aspect of statistics, which is that the normal distribution doesn't necessarily connote anything normal, except for the fact you could probably assume as a mnemonic that it is something that is widely used. A normal distribution, all we're illustrating here is we're using the plot dist function to draw what a normal distribution looks like. It's also known as the bell curve. Any idea why? Well, it looks like a bell in a way. And the point we have here, if we look at this function, it's like many others. You want to put this the type of the distribution in parentheses, but I'm sort of entering it out. I put it in separate lines. If you look at these little bars here, you can see that that's a carriage return, a CR, which means that I just press enter afterwards. And the little argument here is you can tell the computer, you can tell R what kind of distribution it is, and then the degrees of freedom that are used, which is another way of saying what's the sample size that you're using. Again, remember, you can always use this question mark and then do, you should be able to do this if you have any questions about the, you know, if you want any further detail. Keep in mind, as I've said before, R is case sensitive, so dist is, as you can tell, it's a capital letter D. Yeah, what they say, plots, you know, it's a simple kind of plot. So notice that they say it's a string identifying the distribution. If you look at these, the help file. So this is a good, occasion to look at a help file. You have a description, usage, which is simply the syntax, what the syntax looks like, and then the arguments, which is everything after, between each comma, and it has a little label here. So this first function, this is dist right here. Well, it's called a string identifying the distribution. That tells us that this is the reason we're putting it in quotes. A string is simply text. A string function is something that you do to text. So what we're telling the computer here is we're identifying this as a normal distribution. That's basically it. Let's see what else we could say here. You know, there are quite a few other options. It gives you other ideas. We'll look at other kinds of distributions as well. Yeah, we could even look at a chi-square distribution, for instance. Let's just put that in for fun. Even though it's not part of the question, I just want to show you this is what a chi-square distribution looks like, for example. And as you can tell, and I'll use the same n here. I think it's good for comparative purposes. It's different than the normal distribution, right? And here's the point, which is the df simply tells us, you know, what our sample size is. And what happens when we increase the sample size? Well, we can remember, if you want to look at prior plots, you can just toggle backwards. It's hard to tell that we're looking at different plots here. Why? Well, because they look identical. In fact, you know, we can even plot the normal distribution. Let's just put in a number. Let's put in 100. It looks identical. Okay, it's thinking a little bit. See, sometimes R is not even responding. This is one thing about RStudio, is that it's sometimes a little bit slower when you try to do functions or commands. Okay, it did it now. Looks identical. I'm going to actually clear all of these because there's nothing really that useful. But so what happens to the distribution, and if the sample size increases with the normal when you specify the normal distribution? It's same. All right, ça plus change, ça plus la même chose. As they would say in French, the more things change, the more they stay the same. So it's the same, they say. Well, that's the story of the normal distribution. Now let's look at the t-distribution. Keep in mind, if you look at the modules, something happens with the t-distribution. Let's first run it where we have a sample size. It's relatively small. We'll increase a little bit. And here it is even being larger. And then I'm going to put in a little extra line of script here. And we'll specify to 100, and we'll see how long that takes. Okay, but look at this. Let's go back to the beginning. Dot, 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 dot. In fact, if you look at the difference between 49 and 100, that's barely a difference. Now let's do 100, and this will take a while, and we'll do 1,000. Do you think there's going to be even a huge difference? Remember, we're increasing this tenfold. There's a huge difference here. Well, let's take a look. That is such a slight difference between 1,100. And then when we go from 100 to 49, that's not a very big difference. But when we go from 49 to 9, that's a big difference. And 9 to 3, even bigger. Well, what does this say? Well, as the sample size increases, the t-distribution looks a lot like the normal distribution. In fact, let's look at the normal distribution at a sample size where we specify 49 degrees of freedom. Remember, this is 49. This is a normal distribution. Oh, sorry, shoot. I didn't mean to do that one. So I'm going to remove this one plot. So if you want to remove a single plot, you do that little stop sign there. I wanted to put a normal distribution here so we can compare a normal distribution with a t-distribution with a different sample size. Okay, so here's a normal distribution with 49, an n of 49. That's a t-distribution with an n of 1,000. The reason I'm showing you this is that a t-distribution, as the n gets larger, becomes normal. It becomes a normal distribution. It doesn't technically become normal. But the normal distribution, so again, here is the t-distribution at 3, 9, 49, 100, 1,000, And then we're going to move back down to a normal distribution with an n of 49. There you go. So the point is, and here it is, around an n of 30, more or less, you want to use a t-distribution for smaller sample sizes. For statistical tests, and your software already accommodates that adjustment. But as the sample size increases, you can use the normal distribution. So those are the two properties of the normal distribution. And we talked a little bit about critical values. We use a z-score to look at the standard normal distribution. And here's the other function, Tdist, which is we're no longer just plotting distributions, but we're also looking at probabilities. So this is the the probabilities at certain benchmarks, right? So this is if we look at the critical values, the z-scores at -2 and +2. What are the probabilities of lying or under those of a value, you could say, of a statistical test being under those curves? Well, here we see that it's about 0.05. And those are the critical values. Now, this is kind of an interesting, I'm going to diverge a little bit and just sort of talk about the syntax, because this is sort of my bailiwick in terms of what we focus on in this section a little bit more. This makes use of something called the C function, or the combine function, which all it does is it combines two values here, which are separated by commas. The C function is a generalized function in base R, which basically says you're just combining things. So for example, I'm going to do sentence. I'm going to define something. We're going to use the assignment operator. And I'm going to combine hello, comma, world. Now actually, we're going to do something else. We're going to do A and B. And we're going to define A as a string of hello. And then we're going to define B. This should work. I don't know if I need parentheses here. We'll see. And we're just going to define this as C. And you're going to print C. So we have hello, we have world, and then you combine those two objects. And you can see right here, it's a character vector. Vector is simply a line, you could say, just a line of elements. You're going to print that right here. And what do we do? Well, we have something with two elements here. That's the combine function. All it is combine these two little elements right here. You can do this with numbers. You can define a sequence of numbers. But the C function is a very common one. And here's just an argument that makes use of that. What it's saying is you're doing the probability distribution of within the normal curve when you have when you're more than 2 z-scores away from the mean, the average, above and below. And what's the probability here? Remember, probabilities, as we learned, is bound between 1 and 0. And this is an interesting fact, which is that this is the reason, we're a little persnickety about telling you that you have to have you can't go above 1 when you define probabilities. Well, that's what you see here. I just want to make sure I was still recording. Good. Okay, I am recording. I got a little paranoid there. But the point is, when you have a normal distribution, and when we talk about tests of significance, we're always talking about areas under a curve. A two-tailed test is defined by a value that is at the tail of the distribution, that has an extreme value. Yes? Okay. Hopefully you can hear me. Good. Okay. Thank you. All right. So we're just going through some of the functions here in today's section. I talked a little bit about the combine function, and we're looking at the probability distributions here. So the question here is, what is the probability when we have a t-distribution? When we looked at the normal distribution, regardless of the sample size, we see that the normal distribution is defined by a z-score. It basically exhibits these properties, we could say. Now, let's take a look at, the reason we went to the t-distribution and identified the sample sizes. You'll see something interesting here, which is that if you have a smaller sample size, you'll see that critical values, these probabilities are a little bit larger when the sample size is small than when they are for the normal distribution. So, and then if you do it for a slightly larger sample size, okay, these probabilities are a little bit smaller. And then when you do a sample size of 49, this is where you approximate when you get close to the normal distribution. The point here being, the smaller the sample size, you have to use different critical values to define your probabilities with the t-distribution because the tails are a little bit fatter. You're going to overstate your, the probability of something being, of a value being statistically significant because 0.07 plus 0.07 is 0.14. So your critical values are going to be a little bit wider for the t-distribution because you have more area at the extremes of the curve. All this is just more just to illustrate the fact that when we use smaller sample sizes, you have to use different critical values than when you would if you just use normal distribution. Now, that's the p-distribution function, the pdist function. Now, the qdist function is sort of asks a different question. Again, you still see the same, structure of the argument, right? You have the distribution, which is identified by a string. You have the sample size. Now, we're defining not just the critical levels, but we're just identifying the probabilities. Right, so the question here would be, what are the lower and upper t-values corresponding to the probability of obtaining a t-score in the middle, 95% of a t-distribution based on a sample size of 4? So here we have 4. So the degrees of freedom is always, you just add 1 for that for the t-distribution. And then what are the lower and upper critical values if the sample sizes are 10 and 50 respectively? Why do the t-values differ? So here you're looking at you're actually getting the t-value, the t-statistic, and you're looking that correspond to a particular probability. So if you look at this first one, right here you see the t-statistic right here. And here you see the probabilities. So for a small sample size, here's the t-value, t-statistic value that corresponds to a two-tailed significance test of means. Now, as the sample size increases, you'll see that the t-value also changes, right? It gets lower. In fact, it gets a little bit closer to 2, right? If we get it even larger, for the n of 50, look at that. It approximates the normal distribution. Here you have approximates the z-score of plus or minus 2, and that's the probability right there of getting a statistically significant result. So the point really is that this is really more to illustrate properties of p-values and of functions. It's also a very useful tool for statistics because let me see if I can get a textbook here, and we'll see if some textbooks still do this. I'm revealing perhaps my age here, but a lot of them, yes, here we are. A lot of textbooks will make you do this. They'll make you look up, what is the probability for the normal distribution if you have a certain p-value, blah, 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 blah. Well, that's what we don't have to do that with this computer, with these functions. You can actually specify the probability and then derive and then estimate or calculate the probability here. It's still useful to look at the tables here, I suppose. And they do have it for different distributions. Let me see if I can show it to you for the, and there are many distributions, by the way. So here it is for the normal distribution. It will give you the p-value, if I can show you the distribution right here. But the point is, that's all we're doing is we're just saying, okay, given this probability, what's the corresponding t-distribution, and as well as the sample size. that this is for the normal distribution, which if you recall, the sample size doesn't matter. So that's why they don't have an N here. Let's see if they have the T-distribution. Yep. And here's the T-distribution, for example. And what they specify is here's the N right here, and then you have different probability levels. I suppose for pedagogical reasons it's useful, but it's great that we have computers to actually give us beautiful graphs to illustrate this. Let's dive into the data now. I don't think that's, to be honest, when I do statistics, when you become a data scientist, when you do this in your own work, if you are going to do applied data analysis, when you work on your final project, for instance, we're not going to deal a lot with these probability distributions. Now, if you really want to write your own functions, you want to write your own statistical commands, this is useful stuff. Also, it's extremely important for theory. I'm going to get rid of these plots for now, and we're going to dive into the data. Well, we don't have in our global environment the data, do we? Well, I'm going to do something. I'm going to look at what's our working directory. Well, look at this. Where we have in our working directory, we have two elements. I'm going to show you a little something because why not? We're doing a lot of the similar things. Remember I showed you the combine function? Well, the nice thing about R as a programming environment is the directory function will give you what's in your current working directory. And as you see, what we have in our problem set folder on our desktop, I'm going to move RStudio, we have our problem set. Oh, I wanted to say to anyone else joining us, I cannot hear you for audio reasons, so feel free to use the chat function. I'm keeping my mind here. I see that there is a question. Thank you. Text me any questions you might have. So the question here refers to finding a t-score in the middle, but the distribution reference is 0.975. Why are the numbers different? Are you referring to the syntax or are you referring to the problem set assignments? Oh, you're looking at this. Is that right? Why are we specifying this and this? All right, I'll show you. Yeah. All right, so this is interesting. Okay, it's a two-tailed test, right? Because what this does is it provides us with the probability of 0.05 for each tail. So 0.025 times 2 is 0.05, and that corresponds to 95%. So I'll just show you. Let's see. Actually, and by the way, the reason why we have 0.095 is that's the remainder, right? So that's everything else left over in the curve. What I haven't done is intentionally made a mistake and said, well, what happens if we do this? Well, this is not a mistake. This will still add up to 1. What it should show you is right. So this is the probability at the 10% level, in the sense that a two-tailed test. What's the probability of getting a 0.1, a p-value of 0.10, which is not statistically significant according to conventional standards, but people sometimes report it. But the point is that it's a two-tailed test. Now, you just got me curious, which is I'm going to violate this argument here and make our probabilities add up to more than 1. Well, doesn't make any sense. The area of a probability distribution, as we know, one of the fundamental rules of probability is that it's bound by 0 and 1. That's the probability space. We'll see what happens if we just define a probability space. Yeah, so if you notice here, it seems somewhat, it'll give us the t-distribution, the t-value for the negative value of a 0.05 on the left tail, the lower tail, and then it'll have this infinite function on the right tail. I don't know what that means. It's probably just an error command. It won't even give us any t-value here. So the main point of this function is just to look up t-values, and it's two-sided. So thank you for that question. This is like one of those assumptions that we tend to make when you do statistical practice. It just sort of, I don't know, almost always we're doing two-sided tests, even if we're testing one-sided hypotheses in practice. Probably because most people are suspicious of p-values as it is, and it's harder to get a two-tailed test. It's sort of, it's a lower probability. Anyway, let's make sure that adds up. Oh shoot. Is there something wrong? Okay, so what I have a couple errors, if you notice here. I just want to show this to you because this is something that happens to quite a few people. If you see a plus sign at the bottom, it means that the computer recognizes that your argument is not finished. Well, what happened here? I forgot to add an extra close parenthesis. I'm going to press Control S and save my syntax. And then I'm going to press Escape to get out of this and tell the computer, actually, I made a mistake. But the point is, if you find yourself where you're running script and then you all of a sudden have this plus sign and you want to get out of it, just press Escape. I always like to type what I do anyway in this console. And let's just make sure we got our T statistics that are correct. Well, that's not right. What did I do wrong here? Oh, okay. I put 0.095. Control S. See, the devil's in the details. All right. So another point, I guess, to make while we're still talking about t-distributions is, of course, when you talk about statistics, t-values, they're simply the inverse of one another. If we're talking about a two-tailed test, the t-value corresponding to the same positive or negative distance or have the same absolute value, right? So a negative value is negative 3.18, positive 3.18. Okay. Any other questions about statistics, about these distributions? Okay, great. We're going to go to welcome. To all of you newcomers, as you join, I just want to, as each of you join, I just want to emphasize that you'll have to chat to me your questions because I actually can't hear you for some reason. This is just a technical difficulty. One of those things that arises when we deal with Zoom. Let's actually go to the data analysis part. Okay, I was going to show you something what I think is kind of cool. I talked a little bit about objects, had a little disquisition on that, but I'm going to do Control L. Control L will clear your console. I like this because I like to start off with a clean slate. I'm going to use this directory function to define to see what the objects are in a directory. Now I talked a little bit about strings, the string function, and the combine function. Well, this is actually, you can actually define this as a vector with two elements, right? So let's define D as the stuff in our directory. Well, look at this. Just as we defined hello world with two characters, here we have two characters. That first one is our data file, the second one is our script. And you can actually, now you can do data, you should be able to define as the, let's see if we can do the index here, should be able to define as a first element within, no, maybe if you just try it. Hold on. If you define as a first element, no. Well, that's neither here nor there, but the main point is, if you look, you can define even objects in your working space as, elements in your working space as objects. So if you want to say, mess around with that, you can do that as well. But I'm going to actually do it the old-fashioned way. Well, here, we'll do this. We're going to print our elements right here. I'm just going to copy and paste this because this name is not going to change. And then you're just going to do the load function. Copy. We'll talk a little bit about indexing. What I wanted to show you is you could actually index, you could say, well, I want to select the first of that element here, but it's kind of a moot point when you have two elements in your working space, and it's actually probably better practice to simply define your data file. Keep in mind, as usual, everything is case sensitive. So we have capital employed, capital ACS. ACS is the American Community Survey. I was actually asked to fill this out. It's developed by the Census Bureau. And some people were asking about getting the census data. We talked about this last Wednesday for your final project. I recommend you use the American Community Survey. So let's load these data. And here we have it. And you can see that it recognizes a data frame. Here's the name. Here are the observations with 10 variables. So, and what I want to show you, I don't think I've ever really shown you this. If you do this little tab here, you can actually look at you can look at these variables. I don't know what happens when you have more than 10 variables. But this is really useful to actually see because you'll see how the data are read in. So this is useful for your final project because sometimes when you read in variables, they're not what you want them to be. Right? But isn't this beautiful? Look at this. You don't even have to use the view function. You can see this is sex or gender is a factor variable with 2 levels, male, female. It takes on, it looks like they're identifying it they're assigning it with numbers, 1 and 2. Age is numeric, right? So this is actually very useful shorthand just to have a glance at your data without having to use that view function, or the head function, or the tail function. Probably not as useful if you have more than, say, 10 variables. All right, so let's remove some of these objects here, right? And I want to show you this to you. If you use the up and down arrow, you can actually go through your previous commands. So I'm just pressing up here. And the reason this is useful is that, you can, if you want to remove each object separately, you can press up and then just do that. So what you see now is I've only, when you press Control L just to clear the workspace, but of course those commands are already in your console. They're in your history, and you can see that right here. Right. So here we have the data frame. And when we talk about tests of means, we're going to talk about the t-test. Just a simple basic test. I'll walk you through this first. Keep in mind it's a, if you remember from class, it's called Students T-Test because it was created anonymously. So a lot of statistics is historic in the sense that they're named after people. If you become famous and you develop a new technique, you will have, it can be eponymous, as it were. It can be named after you. What you'll see actually, though, I want to show this to you, is the Students T-Test is in the stats package, but we also see that it's in the Mosaic library. And that's important to remember because Mosaic, what it's actually doing is actually, as I mentioned earlier, it uses what are called dependencies. It incorporates a lot of other functions elsewhere, and a t-test is a fundamental statistical test. And for historical reasons, out of sort of credit, we call it Students T-Test. I have a colleague who created a sensitivity analysis, for example, and he wasn't sure what to call it. And I said, why don't you just name it after yourself? He was too modest to do that, I think. He did a very simple kind of technique, but this is quite often the case. Student isn't the real name, as if you recall from the module, but it's a, if you talk about t-tests, it was developed by someone who was anonymous because he was working on, he published it under the name student, the pseudonym student. Right, so this is just as a sort of as an aside, a wrapper function. They call it a wrapper function. A wrapper is simply, if you open a candy bar, it has a wrapper. The intuition here is this is actually such a base function, it's in base R, that Mosaic is using it, but they're kind of wrapping it within the Mosaic library, the Mosaic environment, to make it easier, more accessible for you. And the reason I mention this is that when you use Mosaic, remember that it goes back to this term modularity. The more things change, the more things stay the same. That seems to be the theme today. But it's a theme in good programming practice because you'll see that everything in Mosaic starts with the tilde. They want to express everything as a formula, which is they're saying the test for the variable income using the data employment with this, whatever this is, what is mu? If we scroll down, you can figure this out. Right. Okay. So right, and I just want to make sure that I was correct here. So the reason you use mu with assigning this value is because it's a two-sided test with a null hypothesis that the average income in the population is 35,000. So mu specifies the value for the null hypothesis. So here you're testing, you're against a null that you've specified. I'm going to clear the plots here because those are no longer relevant. So this is what the output looks like. This is canonical. This should be intuitive. After a while. What does this show? Well, a one-sample t-test. Does this question say two-sample? No, good. Okay, it did say. Sorry, it's a little hard for me to see. A one-sample, two-sided t-test with a null hypothesis that the average income in the population is $35,000. What are your null and alternative hypotheses? What do you conclude? So this output is canonical no matter what stats package you use. Keep in mind, the reason we showed you what t values are, degrees of freedom, and p values are, is this is the core information of any statistical inferential test. If you're writing it in text, you'll say this is statistically significant. You'll give the t value, and you'll specify the degrees of freedom, and then you'll give that p value. Well, what does this show? Well, p value is less than 0.05. And the alternative hypothesis is that the true mean is not equal to $35,000. So what does this mean? Well, I guess I'll give you the answer. It suggests, and we can actually even see this if we look at the variables. So if we look at we didn't even do fab stats. I'm sorry. I'll show you. If we look at the fab stats here. Oh, I hope I repaired the syntax here. I think I did. This is one of the few changes I made. There should always be a tilde here. You can see that the mean income here is 45, and the range is from 0 to. Do we have a maximum? Min? Yeah. To 382. So keep in mind these are in units of thousands. And if we look at the data frame, let's see if we can actually see that too. Yeah. Right, so you can see that these are in units of thousands. So I'm sorry, I sort of skipped over the favorite stats function here. But typically whenever you do a statistical test, look at the data first. I mean, that's just typically good practice. You want to see what the data look like. You want to know what the units are. Now, when you do the t-test, then it's easier to interpret, right? Because you're saying, okay, well, you can interpret it in the same units here. And what are we doing here? We're basically saying, is the income true mean equal to $35,000? Well, this doesn't seem to be the case. In fact, the true mean, we're confident that the true mean lies somewhere between 36,000 and 46,000. And that's our 95% confidence interval. So we reject the null hypothesis that the true mean is equal to $35,000. Now you can also do something else. Well, here let's kind of mess around with this. Let's say Does the true mean equal $46,000? You know, let's see. No, it doesn't seem to be the case. Right, and here you can see, oh, sorry. So here we fail to reject. So here we see a lack of p-value. So we fail to reject the assertion that the p-value is not equal to $46,000. Why is that? Well, we can see quite clearly that 46 is within our 95% confidence interval. So we can't rule out the possibility that the true mean is actually $46,000. In fact, let's just get, what do you think the p-value will be if we test the null hypothesis that the true income is $47,000? Well, here we see it's, I guess, statistically significant. So the point here is we can rule out that the true mean is equal to $35,000 because it lies outside of the 95% confidence interval, just as we did when we asserted that it was 35. Does that make sense? So we don't always do this, but sometimes we have a hypothesis that we want to test about the true population mean, and we test it with a sample, and we use inferential statistics to do a test to see whether or not one sample, two-sided test to see whether or not the true population mean lies within our confidence interval. It's actually relatively intuitive once you sort of see the test here. You can see that here. If we test the hypothesis that's 44,000, we're going to see that the p-value is even higher. Well, that simply means that we cannot reject the hypothesis that the income is. Notice my wording, by the way. We fail to reject the hypothesis that the income is $44,000. All we're saying right here is that the data are consistent with the hypothesis that the true income is population income is $44,000. We can infer that, and again, that's simply because of that 95% confidence interval. If any data point, any hypothesis that lies outside, with a value that lies outside of that, like even if we use 36, that'll have a p-value that's not significant. Well, it is significant. Okay, probably because of rounding. Oh no, that's correct. But it's so close. If you look at the rounding, though. Sorry, I did a little error in rounding. So here we reject the hypothesis that right. We reject the hypothesis that the income, the true population income is $36,000. But it's very close because here we're talking about a value that's so close to our lower bound of our 95% confidence interval that the p-value suggests that, well, actually, it's more likely that our income is $36,000 than it is, say, the true mean is just $10,000. This is going to have a very high, very low p-value rather, which means that we definitely can reject this to be the true population mean. So I hope that makes some sense. So okay. So if we have the output, so the next question is, if we have the output from the one sample t-test in question 2, plot the critical t-values using a t-distribution model for the sampling distribution, what is the probability of obtaining a more extreme value than the one we actually observed under the assumption that the sampling distribution is centered on $35,000? What is this probability called? So again, we're going to test this hypothesis that the true population income. I'm going to clear the console, Control L. I'm going to rerun that syntax. So here we have the output. We have the t-distribution. We have the degrees of freedom. We have the p-value. And we have the alternate hypothesis. So the null hypothesis is that the true population mean is equal to 35,000. The alternative hypothesis is that it is not equal to 35,000. Here, the p-value suggests that we reject the null hypothesis. And we have a confidence interval. of 36 to 46,000. So let's look at this probability distribution right here. Well, how did I come up with this right here? Well, you have the t-value, corresponding t-value from this outputs that we just plotted with these degrees of freedom. And what this shows you is this shows you the probability of having this value that is that extreme or more. So again, what we can do instead of looking at probability tables is we can actually take t-values, we can plot those under the probability distribution, essentially to test our hypothesis. And here, we reject the hypothesis that our population income lies within this confidence interval. And the two-tailed test shows that this is a pretty statistically significant probability that, we're reasonably confident that our population income is not 35,000. And we simply plot that by taking our values here, our t-values here. Okay. Now we can do another kind of test using a different option. Not only can we test whether or not our data are consistent with a hypothesis about income, but we can also test whether or not it's we can do a one-sided test rather than a two-sided test. So here, so to use the example, right, an economist at Stanford thinks the average income is $45,000. You're pretty sure that it's less than this amount. So if you want to do a one-sided, one-sample t-test, I said before, we often don't do one-sided tests simply because the probability of getting a one-sided test, how do I put it? You're simply, we'll talk about that later, but it's more canonical, you could say, to do two-sided tests, just simply because I think it's a more you use more extreme critical values. I'm going to clear the plot, this plot function. But if you want to test that, so now what we're doing is if you want to test a one-sided hypothesis, which is, I'm going to test a hypothesis that the income is less than 45, that the true population income is less than 45. And what do we do here? Well, we fail to reject the hypothesis that the true mean is less than $45,000. Right, so how do we come up with this? Well, we can see that the p-value is not statistically significant. So, oh, and here we see the negative infinity, by the way, to this, 45 criterion. The reason is that this is one-sided. So I guess what happened before when I sort of created the value, the probability values that equal greater than 1, it simply just sort of rejected the value of greater than 1 and just treated it as a one-side probability distribution. The point here is that you can test whether or not, you can test a specific hypothesis. The default is that the alternative is a two-sided. Now, if you want to plot this, you can take this t-value with these degrees of freedom, and you can plot what the distribution is. This is simply a visualization of the probability of getting a value this lower or more. And you'll see that this is at the 8% level, you could say, but it doesn't achieve statistical significance. So you fail to reject the null hypothesis, which is that the income are not less than, that the true mean is not less than this value, if that makes sense. Let's see. Yeah, okay, so I showed to you earlier this combine function, right? So we can look at this before, right? This was sort of a subfunction. You can combine values. This is more useful for other functions. Again, this is sort of like looking up table. You know, you could do this in tables, but if you want to say what is a probability with a z-score of 1 or higher, you have a 16% probability with that z-score. So here you can just do a one-sided probability test. You can do it with a normal distribution of 1.5. Notice if the negative specifies the lower tail, positive specifies the upper tail. If you want to do both, if you want to have the probability distribution of less than 1 z-score and 2, then you can get the 2 different probabilities. This is not common to do. Typically what we'll do is, you know, the standard test of significance we'll do here is we'll do this right here. We'll have this value. This is, you know, equals about to 0.05. There's some rounding here. Now again, I think I showed this before, but you know, if you want to find the critical values, so keep in mind, you start with the critical values. You can find the probabilities, or you can derive the probabilities from. You can derive the critical values based on the probabilities. So let's take a look at that. Which one did it plot? Oh yeah, okay, good. So the first one was, what is the, okay, if you have a probability of 50%, what is the critical value? 50-50, right? So a p-value of 0.5 is nothing. If you do the normal distribution, you can do the standard probability of 0.05. There it is. And notice it does it on, looks like it'll do it for one side. And if we do 0.95. Any questions, by the way? Oh, that's a great question, Patrick. Thank you. So someone Patrick just asked, why is 8% not a significant value enough? This is a wonderful question. Thank you for asking this. Well, this is the thing. It's good. It's not that bad, right? You would think 5%. It's because of tradition. Notice I mentioned the student's t-test is out of tradition. The reason we have a p-value of 0.05, and we typically often use we'll use two-tailed tests, it's convention. Nothing really beyond that. But if you want to get published in a scientific journal and you show an 8% p-value, it's not statistically significant. That's what they're going to say. Now, this is one reason that p-values are pretty controversial, because if you look hard enough, you know, there's a saying, if you haven't found a p-value that's statistically significant, you're not looking hard enough. Because in fact, if you keep looking and looking and looking, you can actually commit what is called a type 1 error. You can find a statistically significant result that at the 5% level, at p equals 0.05, that is not actually true. It's a false alarm. Now, 8%, it's, in my opinion, and many people's opinions, is not that bad. In fact, often people will define several critical values, several critical p-values in terms of probability. Typically, they'll do 0.001, 0.01, 0.05, and sometimes 0.01. And these are identified through, you know, a statistic that is that significant. We'll have 3 asterisks, 2 asterisks for the 1% value. 0.05 is often 1 asterisk, and then often we'll do what is like, I can't really type that here, it's a cross, you know. So it's typically identified as a cross. The jargon I'll often hear is marginal significance at the 10% level, trending significance, but canonically, it's not statistically significant. Now, where did we come up with 5%? R.A. Fisher actually wrote somewhere in the 1930s or so, 5% seems to be about right. And then we just sort of stuck around with it. There's a nice saying, though. If there were an 8% probability of finding a pot of gold behind a tree, would you take a look? Yeah, probably. Right? I mean, 8 and 5% quantitatively aren't that big of a deal. And I think that's why visualization really helps, because you shift that probability distribution over, it's not that big of a deal. So long story short, it's convention. There's another saying, God loves a p-value of 0.08 as much as 0.05. I don't know, there are a bunch of quotes on p-values I can cite. So it's not enough because of convention. It still warrants something. And if I were to report it in a study, I would still report it. I think it's useful. Often in my own work, I often report not just in terms of statistical significance, but in terms of that confidence interval, that range of plausible values, because that gives us a better idea of what's going on rather than whether or not it meets some arbitrary threshold. Does that answer your question? Do you have anything else about p-values? Feel free to ask. Where is the line drawn for significance 80, 20, 70, 30? I'm not sure what was meant there. So okay, well, p-value so if you're asking whether a p-value of 0.3 or 0.2 is not significant, or if that's considered significant, it isn't, right? We consider a p-value, typically a two-sided test, to be 0.05. So if we do a t-test, if we go back to our output, let's go to actual data. We're testing the hypothesis whether or not the population is equal to 35. We'll see that the income of 35 lies outside our 95% confidence interval. That's, how do I put that? The probability distribution, a p-value right here is 0.02. That's considered statistically significant. You can almost say highly significant, but if that p-value were 0.5 or 0.3, it's not significant. If you notice, sometimes I'm talking about percentages, and then I'm talking about proportions. Yeah, thank you. You're welcome. We'll often talk about something in language or even writing up analyses. Sometimes it's quite difficult. Here's a great book, actually, Writing Statistics, writing about multivariate analysis, because it's sometimes difficult to put into language these mathematical concepts. One way of expressing it is something is, if I'll express this linguistically. We find that we reject the null hypothesis at the 2% level because our p-value here is 0.02. So we'll sometimes talk about probabilities in terms of percentages. So that's probably, if I mentioned that before. Typically, though, if you're a scientist, you are on the hunt for a p-value less than 0.05. The lower, the better. There is a whole debate about this called p-hacking, which is the idea that scientists are motivated to massage their data until they find a p-value less than 0.05, and then they stop analyzing the data. What we try to do to prevent that is we will often come up with a priori hypotheses. We'll define whether or not it's exploratory, or what's increasingly common is something called pre-registration. You'll publicize online, I'm going to test this hypothesis, and then I'll look at the data. But if you just look at the data, you're gonna find something that's significant at some point. But the core test here is, if you want to do a significance test, you can test whether your sample mean is equivalent to a hypothesized population mean. You can test whether or not the alternative is higher or lower than that, and then you can plot various t-values and other distributions. Yeah, let's look at the default here. We'll go for sort of a hypothesis testing for a one-sample t-test. The default is actually the null of 0. And you'll see that that's not significant for a one-sample test. This is why you want to probably, specify this. Here it is with a null of 8. You'll see that the p-value is close to 0.05. Sorry, 0.5. 0.5. Yeah, so this is also useful too. I didn't show you that you can also test whether a value is greater, or, you've got one-side test. Is a value greater than 10 for the hours a week? So is the population mean greater than 10? Well, here we reject the null, that it is not greater than 10. So we actually believe that the true mean is actually greater than 10. Yes. Now this is more often than not, if you're reporting data, you just really want to report to the world. And we see this with polling. This is actually a great time with the election. We talk about margins of error. Polls show different results, don't they, right? Well, a poll is a sample, a small subset of the American population, a simple random sample that we try to generalize to the population, but we never really know. And that's often expressed with a margin of error. And this is where, more than anything else, this is where we're going to see, where you're going to see even in the press, these 95% confidence intervals, margins of error. So if we look at the hours per week, when we use these data, we have the mean, and we have the lower and the upper confidence interval. So we're seeing that in our sample, we think that there are, if that is, I think that variable hours per week, the number of hours you work per week, on average, it's 38.5. The lower end, it's ranges from 37 to 90 to around 40 hours a week, and that's about where the population average lies, given our sample. Now, of course, the 95% confidence interval, you were asked about, how do you develop a 70, why do we use 95% confidence intervals? Well, it's because a two-tailed test with a 5% significance level is canonical. It's what we use. That being said, we can be lax. We can do an 80% confidence interval. And what do you see? Well, you see that, you simply see I guess you could say a different, benchmark. You could see, your 80, so you're simply specifying, I guess, a different confidence interval. The 99% confidence interval, you'll actually see is a little bit, let's see if we compare. So I want to show this to you. If you can sort of see these confidence intervals, you see that the canonical confidence interval, 37 to 30, about 9.89, is different from this level too. Well, what's the difference? Well, it's a little bit truncated with the 80% confidence interval. If that's right. I'm sorry. No, I'm right. It's and it shifts a little bit. And the 99% confidence interval is between 36 and 40. So depending on your significance level that you want to specify, your confidence interval will also shift. Typically, it'll be, I'm trying to understand why I'm trying to see if the confidence interval is shorter or smaller. Well, it's hard to tell the absolute value of the confidence interval here, but typically the higher the value of the confidence interval, it typically means that you're going to have a broader confidence interval, because you're essentially saying, how do I put it? You're specifying the probability of statistical significance at 1% if you do a 95% confidence interval, which means that it'll be a little bit wider, a little bit less precise. So you're increasing the type 2 error, you're decreasing the type 1 error, false positives, because you're specifying a true confidence level there. I hope that's clear. If not, the main point really is, canonically, the default, in all practice, you're going to use the 95% confidence interval. If you do anything else, people just start asking questions, because think about this. If I just started speaking to you in Spanish, it's going to be confusing. Well, this is part of also the reason we have canonical, keep referring to canonical, historical with precedence about criterion for statistical significance. It simply just facilitates communication. So I think that's all I want to talk about today. We covered probability distributions. We used the plot dist function to look at distributions, different kinds of distributions, right? The normal and the t. Then we showed how p-values and t-values are both related. Then we test whether or not a specific hypothesis of mean is equal to what we'd expect in the population. We also looked at those probability distributions using our data. And then we showed a 95% confidence interval that we can use from our data sample to infer to the population. And we also showed one-sided versus two-sided tests. And I talked a little bit about statistical significance. That's it for today. Any questions? Otherwise, thank you very much. All right. Okay.